In this video, we're going to implement the conjugate beam method in an example to compute the slope and deflection in a beam. So our beam is going to be a cantilevered beam with a 5-kip point load at midspan. We'll add some dimensions to the beam. We'll add some material properties. So the modulus is 29,000 KSI. The moment of inertia is 800 inches to the fourth. That would be a section property. So this, let's just label this as our real beam. And again, the goal is to compute the slope and deflection at point B. So first, we will establish the bending moment diagram for our real beam. It's relatively straightforward, right? We'll have an end moment of 75 kip feet. Then we are going to establish our conjugate beam. So remember, in the case where the real beam has a fixed end, that means it has 0 rotation and 0 transverse displacement. That means we're going to have 0 moment and 0 shear in the conjugate beam, which corresponds to a free end. And when your real beam has a free end, that corresponds to non-zero rotation, non-zero transverse displacement. So in the conjugate beam, you're going to have shear and moment, which corresponds to a fixed support. So in the conjugate beam at point A, that end is free. And at point B, let's actually just call these A prime and B prime to correspond to the conjugate beam. At B prime, that's a fixed support. And then we want to load the M over EI diagram. We want to load the conjugate beam with the M over EI diagram of the real beam. Now, keep in mind, in this case, the moment in the real beam is actually negative because it bends the beam concave downwards or concave in the direction of the negative local y-axis. So therefore, our M over EI loading is also going to be negative. And so we have this triangular M over EI loading diagram, and the resultant of that, we know is going to be equal to the area under that triangular loading. And then the distance to the left end is going to be 5 feet, or a third of the length of a triangular loading. So again, we're trying to find the displacement and rotation at point B in the real beam. So that corresponds to the shear and moment at the right end of the conjugate beam. So we'll use statics to compute the shear and moment at point B prime in the conjugate beam. So if we do sum of forces in the Y, we get that VB prime, which is the same as theta B, is equal to minus 562.5 kip feet squared over EI, which comes out to be minus 0.0039 radians. And if we take sum of moments about point B prime, we get delta B is the same as MB prime which works out to be minus 1.05 inches. So to summarize, we wanted to compute the slope and displacement at point B in this cantilever beam using the conjugate beam method. We started off by establishing the moment diagram for the real beam. Then we created the conjugate beam, which was loaded with the M over EI diagram from the real beam. And we computed the shear at B prime in the conjugate beam, which corresponds to the slope at point B in the real beam. And we also computed the moment at B prime in the conjugate beam, which corresponds to the vertical displacement at point B in the real beam.